What's up, guys? Welcome back to Vanover Machine and Repair. And today's video, we got a real exciting one for you. We're going to be turning this billet of 1045 into a pin boss for an excavator bucket. So if you enjoy heavy turning and a lot of chip removal, this will be a great video today. Let me bring you in close and give you some more details. So the backstory on this job is we have a buddy of mine, Patrick, over at PMV Services. He does exclusively excavator repair, no real machining, mostly servicing, hydraulic, electronic issues, and he's kind of partnered with me to do anything machining related. He also does a little bit of fab work on buckets as well, but I'm really happy to be working with him and doing some of these more machining focused jobs, line boring, etc. So he has a bucket that he picked up at auction that was in bad shape, actually 15 of them, and he's been slowly fixing them and selling them sort of for profit because they're in various states of repair. So for this bucket, it is going to be for a very large excavator. Maybe I'll throw some photos up, but basically it is missing a pin boss. Now the style of pin boss that it is a pin boss that has bolts securing it, and it's an adjustable pin boss, meaning that it has several different shims that you can basically install or remove to account for different type of excavator sticks, making the bucket more versatile. Now in this case, the bolts are broken off and we are just going to be doing a solid pin boss, but other than that, it should be pretty straightforward. Now when we took a look at this job, basically he told me to go out there and measure it and then come back, create a drawing and get this guy machined. And the pin boss on the machine was missing, and the bucket was a little bit rough. Isn't the worst bore I've seen, but wasn't the most precise either. So that brings us to 3D printing. So I went out there and measured it with some calipers and tape measure and basically figured out what I thought the dimensions would be. And because there wasn't one there previous, it's a little bit of extrapolation. So I came back to the shop, I designed what I thought it would be in Fusion 360, and then we went over to the 3D printer and printed it out. Now I had to go back to a shop the following day to drop off an excavator pin for a different job, and so while I was there, I took this 3D printed part, which I printed while I was at the shop the previous day, and I test fit this into the existing bucket to verify the dimensions. And from that, I was able to confirm that this dimension is more or less the same thing that we want. And that's kind of the point that I want to draw here. I have recently adapted 3D printing into my workflow, and you're not always going to be able to use it, but in certain cases, it makes a lot of sense. And in this case, the material for this job is quite pricey, and we didn't have an original part, and the opening was not perfect. So to be able to have a rough idea of what I thought it would be, come back, print one, use less than $5 in materials, really spend no downtime in man hours, and then before I leave for the day, grab the part off the printer, and then test fit it, and then have the confidence I need to go ahead and machine this part and know that it's going to be the right fit. Aside from doing something like this, we could have kind of extrapolated the measurements based on metric standards, test fit the part, and kind of crossed our fingers, and it may have been fine, but ultimately, I don't want to make a second one. And so having this test part not only gives me visual confirmation of what I'm making, but allows me to have confidence knowing that I'm going to be making this once. These prints are accurate enough that I can measure off of these guys and also review my drawing and make adaptations so that I know that this piece is going to fit and it's going to be a successful job. So with all that out of the way, let's get this set up in the lathe and start getting the turning done. We got the part chucked up in the lathe. Before we jump into turning this down, I just want to address our machining setup because it's a little bit unusual and I know I'm going to get comments on it. So when we're making a part like this, the best way to do it is to go ahead and saw this off about 2 inches larger than the part so we can chuck up on it. We don't need the tailstock as support, and then we can go ahead and get this machined in one operation basically, except for the back. But the reason we're not going to do that is doing that wastes like 2 inches on this huge billet, and I actually need the rest of this for another project. And frankly, if we would cut off extra material, we would be too short for our next project. So what we're going to do instead is machine it as it sits with some tailstock support, and then we'll remove that and drill it out. We'll still machine everything in one operation. We'll do the heavy turning with support, and then we'll take it over to the saw and cut it like an 1/8 inch oversized, maybe 3/16, and then we can flip that around and face the back and finish off, and that'll allow us to keep as much material on this billet as possible. So with that being said, let's come in here. We're going to get this faced off first, so that way our puck can have a nice flat surface. Then we'll put the puck back on, and then we'll get to our heavy machining. We're going 1 millimeter off the diameter. Not too exciting. 2 millimeter off the diameter. And that would be 2.5 or 3 technically. I'm getting bored. Are you getting bored? 4 millimeters off the diameter. Actually, that is not 4. That'll be 4 when it hits the step. Here we come. That's 4 right there. It's not bad. Still a little bit boring. So that was 4 thousandths off, 4 millimeters off the diameter. Let's go to 5. And actually, let's speed this up. Here we go, that's 5 millimeters off the diameter right there on the end. And then it'll be 9 millimeters when it hits that step. We'll see if we can get some real fun going then. Tips are hot. Here we go, 9 mil. Now we're having fun. All right, we're trying to find the limit here. We're doing a 12 mil depth of cut, or about a 1/2 inch off the diameter. I have no idea what the feed rate is. This lathe has been converted to metric temporarily. I don't know, maybe it's 10 or 15 thousandths per rev. I don't know. Let's see what she can do. See if we're gonna stall this bad boy. Yup. All right, that was 445 RPM, 10 horsepower motor, and we were taking about a 1/2 inch off. We definitely stalled it, but I don't know about you guys, but I would love to still see 12 mil taken off. So we stepped it down to, it looks like, what is that, 235 RPM? And let's see what we got out of this guy. Let's see what this old girl will do. New insert on there. I bet she's gonna do it. We ain't stalling her. She's gonna take a bite. She's got it. There she goes. That's called eating, my friends. 1/2 inch off the diameter. Welcome to the American pacemaker. Quick draw McGraw on the lever, I can tell you that. We are going to take it all the way to the step. This is full roll, so it's kind of like cheating, but that is what it is. Could be the biggest cut I've taken. back it off after this. I'm satisfied. Insert is buried. Well, folks, I think I'm satisfied. Those are some nice chips there. We're pushing this machine to see what it can do. It's got a nice metallic sound. I'm satisfied for today. I wanted to give you guys some heavy turning, and I think we got it. But I know this machine can do more. I have some ideas. So there will be some even more heavy turning in the future to see what we can get out of this baby, because I think she's got more up her sleeve. But until then, this will satisfy me for now. Let's step it down to a more reasonable depth of cut and get this job finished out. Just a measly 5 mil per side. Decent surface finish for some hot roll. Not too bad. We're at 172 millimeters on the OD, bringing it down to 140, so we got some work to do.
Yeah, pushing some things forward, trying out some stuff. There's a welding opportunity that they have, but their warehouse is only like 10 minutes away from where I live.
$86,000. Spot on the money. Well guys, we got the spacer done and it turned out perfect. Dimensionally, it is really, really accurate, way more accurate than it needs to be. And obviously the finish turned out great. It's kind of a shame because we're gonna hand this to Patrick. He's gonna slap it in the bucket and it's gonna sit outside and rust instantly. kind of begs the question as to why we took the time to get a great surface finish and do it as dimensionally accurate as we did in the first place. And the reason for that is we just want to do as good of a job as we can given the time for the customer. When I started out machining, I would go real slow and I would take a really small depth of cut. And what that meant is I was standing at the machine forever. A lot of times I was getting bad surface finishes and I was inefficient. As I got more experienced, I learned that taking heavier cuts can not only lead to more efficient material removal, but can help improve surface finish. And as I've gotten better and better, I've learned how to be able to knock these parts out efficiently and to make them look great and be dimensionally accurate. Now I have a long way to go in terms of learning every little aspect of machining, but I am really happy with what we were able to achieve here, and I know Patrick's going to love it as well. I hope you guys enjoyed this video, and let me know what you think down in the comments, and we'll see you on the next one.